Hello, and welcome to a short discussion on vehicle network privacy. I'm George Corser. Today we'll discuss established standards, active research areas, and future directions in vehicle network privacy. We will have a short introduction where we'll discuss a number of properties that are general to the entire field of vehicle networks. Then we'll discuss the specific properties that deal with privacy. We'll divide these into three parts: established standards, active research areas, and future directions. And then there will be a short conclusion. Introduction. We'll talk today about the vehicle network model, which is the way that vehicles interact with each other through a network. The DSRC protocol stacks, which there's two of them, and DSRC stands for Dedicated Short Range Communications. And the privacy threat model number 3, which is basically how can privacy be breached using vehicle networks. And then last but not least, we'll talk specifically about location privacy metrics. How do we measure location privacy in particular? The vehicle network model basically allows for two types of communications, at least two that we're going to mention here in this presentation. The first one is vehicle to vehicle, or V2V. This is a short message that's sent between vehicles very frequently, up to 10 times per second, to let them know where they are and so they can avoid collisions. There's other messages that get sent as well, but that safety message is the main one we'll focus on in this presentation. Sometimes a car will, however, pass by an antenna of some sort called an RSU, or roadside unit, and what they might do there is, make the RSU might use the information of the vehicle's location to manage traffic. So it might control intelligent traffic lights or other things like that. It also might go to the internet and use applications like a location-based service, although that's usually done through a cell phone type of a connection, but it could do that also. There are two protocol stacks. One of them is the WSMP, the Wave Short Message Protocol direction. These are for very quick ad hoc connections between vehicles where there's no handshaking required. They're low latency, very small messages typically that are communicated frequently and rapidly. And they are wirelessly also. And that's the V2V or V2I when there's no internet involved. If an application or a vehicle does want to communicate through this system using the internet, they do have to go through the regular handshaking that you would expect in IP and TCP. Everything's based on 802.11p protocol, and this is transmitted in the 5.9 gigahertz range. So you can look up these standards, but the important thing for you to know in this presentation is that there are two protocol stacks, one for quick messages and one for internet connections. The privacy threat model that we are looking at is a three-part model. One is the threat of a person locally, or a vehicle or an antenna set up very close to where the target of the eavesdropping would be, and they can monitor these wireless transmissions to see the location of the vehicle in question. That would be limited to the communications range of the vehicle. The other would be a roadside unit administrator, an RSU administrator. They may have access through their own infrastructure to one or more of these antennas, which could be sensitive to a much wider range than what a local vehicle might be able to pick up. And then last but not least is, if the vehicle is using a location-based service, then the location-based service administrator, the LBS administrator, might be able to use either a map database to identify what the address is that the vehicle is transmitting from, or it might just be able to know the vehicle may make specific queries about what it's looking for. Any of these three entities could breach the privacy of a vehicle, and we're especially concerned with automated attacks, where a computer could just keep on monitoring for somebody. Remote attacks, such as what you might have with an RSU administrator or LBS, and especially when you can't identify who is doing the eavesdropping. And then last but not least, group and colluding attacks, where one or more of these entities may cooperate to eavesdrop. There's several ways to measure privacy. Let's take a look at several of them. First, the theory behind it. Shokri, in his paper in 2010, identified 4 methods of preserving location privacy. 1 is to hide events. 2 is to add dummy events. 3 is to obfuscate the events. And then 4 is to anonymize them. In the case of MAC layer wireless, vehicle networks, hiding is not possible because it defeats safety. If we don't transmit, how can we use the information to prevent vehicles from colliding? So hiding does not work at the MAC layer. Dumbifying does not work either, because adding additional events, adding dummy events that aren't there, adding cars that aren't there, would cause traffic to not flow smoothly, and potentially might cause a car to stop suddenly and cause an accident. So dumbifying does not work. Obfuscating, again, also does not work because we need precise location in order to compute the trajectories of vehicles to avoid collisions. So we can't obfuscate the locations. The only thing at the MAC layer that's going to work is anonymization. It's the only technique that does not defeat safety, although it does have other privacy-related problems. So the way we measure privacy is one way, probably the most common way, is the anonymity set size. This can be measured using K-anonymity, which is Sweeney had introduced. And basically the idea is, if you can't identify which car among K different cars is the one you're trying to monitor, then that car has K-anonymity. Another metric is the entropy of the anonymity set size. If you have 64 cars, then it's kind of a exaggeration to say that you have a 64 level of anonymity. The way that that Shannon's entropy equation calculates it, it's the exponent to the base 2 anonymity. So 2 to the 6th, whatever it would be. So the entropy is a more realistic measure, I guess a more human interpreted measure of the location privacy. And then another way that's commonly measured is the tracking probability. What are the odds that the vehicle that's being tracked has K equals to 1? If it does, then there's no anonymity for that vehicle, and if all the cars had the anonymity set sizes of 1, then all of them would be trackable. So you might say, like, if 50% of them have probability of anonymity set size is 1, then 50% of you have 50% tracking probability for the system. So we try to find systems that have a low tracking probability percentage. You don't want to be able to track vehicles. Last but not least, the distance deviation is a measure of location privacy. Basically, the idea is this: if the vehicles are all close together, even if you can't tell which vehicle is the one that's the target, if they're very close together, it almost doesn't matter. You can just block the road, or you can do whatever you need to do to attack that vehicle. So what we're trying to strive for in some of our privacy protection models is a large distance between the car that is the real car and the car that is the other cars that are hiding the car that we're trying to eavesdrop on. So location privacy metric of distance deviation is another important metric. So we've looked at some of the app properties, the general properties. Now let's look at some specific privacy properties that are involved in vehicle networks. We're going to divide these into categories. One is going to be established standards: safety, trust, and identity privacy. 2 is going to be active research areas. This includes location privacy, historical location privacy, conditional privacy, revocability, trust, authority, decentralization, and anonymous LBS access. These are areas that have been studied. There are papers published on them, and they've been looked at, but nothing has been decided. And then the third area is future directions: map, database, undeanonymizability, how to prevent others from being able to de-anonymize the data, whether or not they have privacy protections; context awareness, and user consent, choice, and control. These are things that are very new or current or future directions for vehicle privacy research. So let's get to it. Part 1, establish standards. Number 1, safety, collision avoidance. We have to make sure that these messages sent between cars are able to be used to compute trajectories so that they can prevent themselves from colliding with each other. This type of an application requires frequent precise location information, FPL information, transmitted by every vehicle. The current standard requires, I think, 10 times per second, 100 milliseconds per heartbeat message or pulse message that's sent by every single vehicle. Some open issues here to consider. How can we reduce wireless network congestion? With all these messages being transmitted 10 times per second by every car, how can we reduce, what if you have a parking lot full of cars? Nobody could communicate. Some people are looking into changing the message transmission range based on vehicle density, but it's still really an open question. Another question is how to handle the deployment as we transition from very few cars with these types of networks, equipment installed, to a saturation of these DSRC systems in all the cars. There's going to be a transition period, and how are we going to handle safety algorithms as we go from point A to point B? The second area to think about is trust. When we say trust, we mean authentication. If a bad actor were to transmit a false, frequent, precise location trajectory, then the traffic flow could be impaired. It could, slow cars down. But it also, if, like for example, here in this picture, if car A thinks that car B is real, but car B is actually fake, car A might stop suddenly, and then the car behind car A might crash into it. So you could conceivably create safety problems there. In order for trust and authentication to work the way it's currently established in the IEEE standards and the SAE standards, is like this. Every vehicle has an identity, a real identity, and there's a digital certificate added to the message, each message, along with the signature for the message. That allows the receivers of the message to authenticate quickly. That's the way it's being done. To reduce latency, safety messages it has been suggested that not every single safety message has to have a signature and a certificate. Maybe just some of them do. The other question is, should we ignore a message if the certificate's not valid? If it's not valid, maybe it could still be a real car, but the certificate's not valid. So there's issues there. Another one, there's a whole bunch of trust issues, and we're focusing on privacy here, but one of them is unforgeability, another one's unframeability. We're not going to deal with all these trust issues here, but they do sometimes affect privacy. But we're just going to focus on the main areas that affect privacy. Number 3 is identity privacy. Some people call this anonymous authentication. Some people call it pseudonymous authentication. We will call it pseudonymity because the word anonymity has a mathematical meaning, and we need to use it as a metric. So we're going to use pseudonymity for this presentation because what we're talking about is not anonymity where you have no name, but pseudonymity where you have a false name. So basically we want to have every vehicle have a false name so that the eavesdroppers can't use, say, the vehicle identification number to know which vehicle is really the one that's at a particular location at a particular time. Of course, in order for these pseudonyms to work, there has to be a pseudonym issued, and for each one of those pseudonyms, it has to have its own digital certificate so that it can sign the messages. The other thing is it has to have a temporary MAC address. So the current standards call for each pseudonym to have a certificate and a temporary MAC address, not like a regular computer or a regular host that has a unique MAC address. That's a big deal. I mean, it's a big major departure from the way things are usually done. And so the question would be, how will cars obtain all of these pseudonyms and certificates? How will they be distributed? What will be the distribution system for all this information? Some researchers suggest that we should have pseudonyms change every 5 or 10 minutes, which might mean hundreds of thousands of pseudonyms per car, or tens of thousands anyway, per car per year. So it becomes an issue if you have multiple pseudonyms per car. So let's move to the second part, which is active research areas. And this goes back to the untrackability point that we were making earlier. If a vehicle only uses one pseudonym, it may as well be the real vehicle ID, because it wouldn't take much time before you could, by following the trajectories of that pseudonym, you could see the pattern of driving, and you could identify who the vehicle owner is. So what's suggested is to have many pseudonyms and some kind of a pseudonym switching technique, so that when cars change from one pseudonym to the other, the pseudonyms are unlinkable. The past and the present one are unlinkable with each other. The way this is done is one of three ways typically. Silent period. The problem with a silent period is it impacts safety. If the car goes silent and then changes its pseudonym, while it's silent, it's not getting any safety protection. Another one is a mix zone. This is where many cars will change pseudonyms at the same time and then mix them up. But again, it's not useful without a silent period. Because of the precision of these locations, you need to have some period where they could be obscured. So you have a silent period or some kind of obfuscation technique. And then the group signature. The group signature would allow groups of cars to travel and use the same digital signature and the same identifier. And so the problem with this is that it may require, if you have one bad actor in the group, it could be a huge complication to get the CRL, the certificate revocation list, to the right people. The other thing would be the overhead is just a lot. I mean, some people think that this group signature method simply can never work because of the overhead involved. So, location privacy open questions. How many cars will each key hold at a time? Can one vehicle have multiple concurrent pseudo IDs that are valid over the same period? That way that they could possibly change from one to the other. But of course that raises the question of what happens if they use both. Then the other one would be, can a vehicle, if they're not in any range of any other car, I mean, they're a safe distance from everybody, maybe they could morph their location with somebody, fake it out. Instead of just going silent, actually broadcast a false message. And then the other thing about location privacy we mentioned before is how far are the fake cars from the real car? How far are the decoys from the target? The distance, the farther the distance, the better the privacy. Now let's talk about historical privacy. Regular location privacy we might call untrackability. You can't follow where that person is or that car is. Untraceability means you can't go back indefinitely as far as you want to find where a person was forever. Historical location privacy, I mean, some of the techniques for generating these pseudonyms, they follow a pattern. So if you know one of the pseudonyms, you can find the past pseudonyms. Historical location privacy would ensure backward privacy protection so that you can't do that. So just because you know yesterday's pseudonym doesn't mean you can know last week's pseudonym. And the question, of course, is when should people be allowed to, to trace back? What should be the authority mechanism involved? Number 6, conditional privacy, we call accountability. Let's suppose there's an accident and somebody needs to find out. They know what the pseudo ID was, but they don't know who it belongs to. There needs to be some method to be able to reverse the privacy protection, perhaps going to the certificate authority and identify who the original owner, the real vehicle ID is there. It could be the certificate authority, it could be some other trusted third party that issued that ID, but whatever it is, there needs to be a way to reverse the privacy. The open questions is, again, who should have the authority to do this, under what conditions. There's legal issues involved, especially who can sue for damages if data is illegally revealed. A lot of these are not technical issues, but they do get a lot of discussion in the technical papers because we want to find solutions, technical solutions to some of these problems. Number 7, revocability. We may find that say in this diagram, car B is not real, but it's broadcasting or transmitting with a real signature, a proper certificate and signature. If this happens, the trust system has failed and we need to revoke the certificate on car B. If this is necessary, we need to have some method of revoking this. It's that simple. The problem again comes to the same questions as conditional privacy, plus how are you going to manage all these certificate revocation lists? They can get to be pretty huge. And if we can, the other question is, if we can reduce the validity period for these NIMs, if they're only 5 or 10 minutes long, do we really need to have long, big CRLs? I mean, how can we manage that problem? This is a problem that has gotten a lot of attention in the research community, but it is still an open question. Number 8, trust authority decentralization. Sometimes you don't want the one entity to control the entire trust system, because then that entity, has absolute power over that, and it's possible that a bad actor could, do some, a number of things to mess up the vehicle network. A lot of researchers have suggested decentralizing the trust system so that there's multiple trusted third parties involved in issuing one of these signatures, and that there's blind signatures and distributed key generation, and distributed certificate revocation, so that no one authority has total control over the trust system. Problem again, how do you handle that? How is it handled over legal jurisdictions? How is it handled technically? This is big areas of research, but it affects privacy in the sense that the overhead can make it difficult to implement other protections. So we'll go into that later. Number 9, anonymous LBS access. A number of researchers have suggested that we should be able to access location-based services, computer programs running on the internet that give you information based on your location, that they should be able to access these programs anonymously. The main method that has been suggested is the use of a proxy, either another vehicle or a server in the cloud. The problem with this is, open questions is, how do we ensure that one layer of the protocol stack doesn't break the privacy protection of the other layer? One researcher has suggested a hooking concept, and that looks promising, but the question is still open. Some have suggested that the physical layer can also be used for tracking, that there's a radio fingerprint unique to each transmitter. So anyway, the bottom line is there has to be some way of protecting anonymity, across these layers, network layers. And then another thing that I recently published a paper on is how to protect the endpoints, the home and work locations, say, of a vehicle, because they're going to go to those locations frequently, and if they do that, then it doesn't really matter all the other privacy protections. The location alone might reveal who it is that's traveling, and the location-based service might be able to determine that. So we need a system for that. These are open issues. A new area that's just emerging now, I just got a paper published on it. It hasn't been published yet, but it will be soon, on Undeanonymizability. The idea is to create a system that can protect against somebody trying to de-anonymize your latitude and longitude coordinates using Google Maps or, say, the U.S. Census location database. It may require application-level defenses. It may require silent periods. There's any number of ways to do this, but all the privacy protections that have been suggested may break down if we don't have some method of protecting against just the location data alone, nothing else. That's what undeanonymizability would do. Spatial cloaking does not work if you have frequent precise locations, even at the application level. For example, if you have this car here, you can kind of see that the 2 dots in the upper left are in one spatial cloak region, and then the second one, only one of them is in there, and then the third one, none of the first 2 are in there. So you could kind of isolate which car is the real car by using its pseudo ID and the pseudo IDs of other cars, and whichever one is in every single snapshot, that's your car. So you can protect against this, but there needs to be a system in place. This is a new area. These two papers here are the ones that I published in this area. So let's take a look at future directions. Basically, there's two future directions I want to focus on. One of them is context awareness. In other applications, privacy is context aware, but not so in vehicle research. It has not been, I haven't found any papers on that yet. There could be some, but I haven't found any. There are times when, for example, your car is close to home and you might want to go transmission silent. There may be times when you are by a government building, say, and you want to go transmission, identity transparent. There might be other contexts when, maybe who's driving the vehicle may have an effect on the context. The idea is the privacy system should be aware of its context and set itself based on the right conditions. Another thing is user consent, choice, and control. This hasn't been researched because we still haven't got all the fundamental details in place, but there may need to be mechanisms that allow the driver to at least consent. Consent would be good, choice would be better, control would be best, but consent, choose, or control his privacy settings. So, you have now seen a brief overview of the vehicle network privacy properties. You've seen the established standards, you've seen the active research areas, and a couple of the future directions. I hope that this has been useful for you. You can see that there's a lot of areas to be researched here. There's a lot of unanswered questions, and I look forward to giving you my next presentation, which will be the area that I intend to explore more thoroughly. Thanks for your attention.